Hi, I'm Alan Lowe, software architect and P4 lead at Nvidia. Welcome to the P4 workshop. Today, I have the pleasure to introduce Yong Feng, a PhD candidate at Tsinghua University, and Dr. Haoyu, a researcher at Futurwei Technologies. In their presentation today, titled "Extending P4 to support runtime programmability," they will discuss a new programmable target and its corresponding programming model that supports runtime programmability of the data plane. Thank you both for joining us today.
Hello everyone, my name is Yong Feng from Tsinghua University, and today I'm going to present our work on a new programmable target that supports runtime programmability. Switches have evolved from fixed function switches to programmable switches, and users can write their own packet processing functions. With the emergence of more and more diverse network applications, it is necessary to update the functions of the switch without interrupting the current traffic. That is, give users the ability to customize the protocol through table and the processing logic at the runtime. There are many scenarios that need the feature of runtime programmability. For example, network telemetry or measurement based on real-time network conditions cannot be foreseen at design time, so it is better to make them on demand at the runtime. Second, many in-network computing functions are not always needed and are resource-consuming, so it is better to make them hot pluggable at the runtime. Thirdly, the change of traffic pattern and network scale makes it necessary to enlarge or shrink a table's width or depth, provision new tables, or change a search key at runtime. Fourthly, for multi-tenant services, modifications for any tenant cannot affect other tenants, but now the service upgrading needs to stop all services. Lastly, device updates can be destructive to the states of state functions. For example, congestion control and caching. This can be avoided by uninterrupted incremental updates. So, as the popular implementation of data plan, what limitations does PISA have in terms of implementing runtime programmability? As for protocol, in the figure, four functions need different protocols and the front parser is decoupled from the pipeline. So when adding a new function with new protocol, the front parsers and the pipeline stages both need to be updated, which can be rather complicated and time-consuming. More seriously, we are unable to add new protocols to parse in PISA, as the fields in a protocol should be orchestrated meticulously at design time. In PISA, the maximum number of ingress and egress stages is fixed, and they are hardwired, so the design space is limited. For example, if one needs n+3 stages for ingress processing, PISA cannot allocate them. At the right figure, insert a new function f3 between f1 and f2 requires to reprogram all the affected stages. After deleting f1, two empty processors are left in the pipeline, which influences the latency. As for memories, when adding or deleting functions, processing logic migration means the associative migration, which is time-consuming and error-prone. And if the size of the flow table is big, there should be more than one processor to implement the function, which decreases the usability of MAUs. So we propose IPSA to solve our problems. Specifically, we use distributed on-demand parser to implement protocol updating, template-based stage processor to implement processing logic customization at runtime, virtual pipeline to improve the flexibility of the original pipeline, and disaggregated memory pool to add, recycle, modify flow table. We integrate the front parser into the normal pipeline. The function module parses protocols that it will use independently. Naturally, PHV in PISA is not used in IPSA. IPSA uses packed window to parse protocols in time, along with processing packets. And when inserting a new function, this architecture can minimize the effect on other functions. Naturally, the processor is not match action unit anymore. and it is composed of parser to parse particles out, matcher to match fields against flow tables, and executor to execute actions. We use the parser matcher executor triad as a template skeleton named TFT. For example, in PISA, we should download the binary executable file to the chip, but in EPSA, we have already downloaded the skeleton into the chip, so configuring the processor becomes downloading skeleton parameters, what to pass, which table to look up, and what actions to execute. Like POF, all about are based on offset and length, so the processing is independent of particles and fields. For example, if we want to use the header length field IHL in IPv4, we should obtain it by IPv4 offset, the internal offset of IHL and length of IHL. We choose an interconnection network to connect all of the processors, so any two processors can be neighbors, different from the hardwired pipeline in PISA. In the left figure, the pipeline is 1, 4, 3, TM, and 6. And now we want to insert function in TSP2 after TSP4, so we can modify the configuration of the interconnection network by adding TSP2 to the pipeline to support the new function chains 1, 4, 2, 3, TM, 6. What we should know is that the interconnection network acts as configurator, not scheduler, as we should ensure the throughput by full pipeline implementation with no excess contention. As for memory, recycling and rebuilding lookup tables are tough problems. If the disaggregates the memory from processors to a shared memory pool like DRMT, a crossbar switch is statically configured for each design to provide interconnection between TSPs and memory blocks. Updates on to cope with the scalability, different crossbar types such as segment crossbar, closed spins, and etc. can be used as a trade-off between flexibility and resource consumption. And the incremental memory and TSP allocation memory can be seen in our paper. We use big bubble updating technique to update the pipeline. For example, TSP3, TSP4, and 5 should be reconfigured at the runtime. Firstly, TSP2 is stopped from moving packs to TSP3 to join TSP3 in time T clock cycles. After that, demo clock cycles are used to configure TSP3. Then the packet flowing resumes. The other TSPs such as TSP4 and TSP5 that need to be modified will take turn when the created bubble arrives. At last, with packet flowing, the front buffer is empty again. The buffer needed for updating is less than 1% memory in terms of the switch buffer. With big bubble update, we can ensure that any packet is processed either by the complete new configuration or the complete original configuration. So the updating consistency is guaranteed along with the updating process. We extend P4 with RP4 to support in situ programmability for users. The workflow of RP4 is, firstly, user customizes the base design in P4. Then with the RP4 front-end compiler, it can be translated into RP4 intermediate representation. In the meantime, the RP4 FC exposes runtime configurable API to the control plane. With the RP4 backend compiler, the error can be compiled into target-dependent configurations. In-situ programming can be done in EPSA control plane. Users can download commands and RP4 code snippet, and the RP4 backend compiler translates the runtime requirements and updates the RP4 AR. Then the compiler provides new interfaces for flow entry modification and so on. Corresponding implementations can be seen on the open source website. We use the level 2 switching and level 3 routing as the use case. L2-3 stage determines whether the packet goes to level 2 or level 3 forwarding. The max stage does level 2 switching and the IPv4 stage does level 3 routing. ACL filters permitted quintuple. Now, users want to add the MPLS function to the switch. They can write commands with RP4 snippet, and the controller can compile the updates and download them into DataPlan, such that L23 can parse Ethernet protocol, and MPLS can parse MPLS protocol and can pop, push, or swap the label. Then ACL can parse IP and TCP protocols out, so the MPLS is inserted into the data plan. In the evaluation, with the 12 process configuration, IPSA spent 12.09% more LUTs and 9.69% more FFs, as there should be more spaces to store the configuration. As for throughput and latency, in the Linux FPGA, PISA can reach a frequency of 153.3 MHz, and IPSA is 110 and 110.45, as IPSA is limited by the multi-die architecture in FPGA, which can be solved in ASIC chip or 3D-SA techniques. In the left figure, the longer latency of the IPSA prototype is due to field and flow table profile fetching, match key assembly, and primitive loading. As for IPSA average pipeline latency while updating, we can see in the right figure that the packet processing latency is relatively steady during update. As for the update performance for updating compiling time, IPSA only compiles the updated code segment, so it takes much shorter time than PISA. Secondly, unique to IPSA is the parameter loading time. Thirdly, as we use Big Bubble update, IPSA's pipeline honking time is only 0.34% of PISA. In summary, IPSA's overall time is 4 orders of magnitude smaller than that of PISA. To summarize this presentation, firstly, IPSA is proposed and is verified in theory and FPGA implementation to support runtime reconfigurability in terms of protocol processing logic and flow table. Secondly, RP4 is extended from P4 to support a user to reconfigure data plan at the runtime. The behavioral model and corresponding compiler is open source. We provide researchers a new target to deploy their apps and support runtime reconfigurability. Please contact us if there exist problems when using the target. And now we are working on providing users with GUI to configure data plan more intuitively. And here is a simple software demo with 3 use cases.
We have implemented software simulator and hardware prototype, and next we show the software simulator in terms of 3 use cases: MPLS tag processing, ECMP support, and multi-tenant function update. The first use case is, the base program supports level 2 and level 3 forwarding, and hosts in different subnets can communicate with each other via C1 to C2. And now we want to add MPLS forwarding to C1, C2, and C3 at runtime. The step is, firstly, download configurations and flow tables. Following above steps, all of the 7 switches are configured. Then we update the configurations of the second switch, A1. Then delete old flow tables in action. Note that operations work when the final submit button is clicked. Now the old configurations are deleted. And next we add new configurations. Update works and then download new flow tables. After updating A1, we update C with MPLS forwarding. The configurations of A2 are the same as those of A1. And configurations of C2 and C3 are the same as those of C1. Update done, then packets are forwarded according to MPLS, not IP anymore. The second use case is, the base program supports level 2 and level 3 forwarding, and H1, H2, H3 can access H4 and H5 only via the top path. And now we want to add ECMP function to switch A1, A2, and A3 to guide packets to other two middle switches. The step is, firstly, download old configurations and flow tables. Obviously, the top switch 5 takes all the load. Then we add ECMP function to A1, A2, and A3 for load balancing. In this case, we don't need to delete any flow tables and actions. Just add the stage that supports ECMP behind node 6 and add related flow tables and actions. Download new flow tables to the new configured switches. Then the other two switches can balance the load from the top switch. The third use case is, the base program supports add and logic and aggregation. H1 emits packets with add requirement and H2 with logic and requirement. Now tenant H3 joins in the network with logic or requirement. The three switches need to support the new requirement. The step is, download configurations and flow tables, including two types of functions, logic and add, for original tenants. Then update the configuration for function logic or. For all the switches, push a new stage back for logic or function. Add a new stage, node 12, which contains logic or and drop actions. New function, logic or, is loaded.
Okay, thank you for your listening, and I'm available for questions.
Right. Great. Thanks. First off, thank you for this great presentation on a very timely topic. Runtime programmability is, well, not a new thing in the computer science domain. It's great to see it's finally being addressed in the networking space. So well done. I did have a couple questions. We'll start with the first one. So I was wondering, from a high level, what was your motivation for creating RP4 as the kind of the interface, instead of, say, either modifying P4 language itself or just presenting RP4 as by itself? Why did you choose to make that distinction? And maybe is there a way that they could actually be one language?
Because we think that the P4K code is not modular coding.
Right.
And we want to make them modular.
Okay. I mean, that's a common complaint about P4s. It's a little bit monolithic. Yes.
Yeah, we want to reuse P4 because P4 is popular and also has a mature community. But on the other hand, P4 itself is incapable of supporting the runtime programmability right now. But we still want to use that, but we find that there's actually a way to just extend it. We can support runtime programmability. So we show the way we still use a P4 program as a front end. Then we can compile it to the RP4 structure. Then it's become modularized. Then we can allow us to add modularized functions to the design. So in that way, we can support runtime programmability.
All right. So does just so I can understand, does the P4 part, like you've specified two P4 programs, one the kind of the before and one is the update, and it does the merge?
Actually, you can start from the P4 design. Then we will convert it to the RP4 format. And from then on, if we do incremental updates, we will just based on their RP4 files.
Got it.
However, you can also directly use RP4 to program that, so that basically provide you two approaches. Allowing you use the P4 as a front end actually allow us to reuse many existing designs. Yeah.
Okay, great. So our RP4 by itself could be standalone. That's good to know. All right. Second question. So I was kind of curious, what is the intersection between your work and P4 runtime? I mean, like this is a dynamic runtime control, and did you extend anything in P4 runtime, or is the control concept in your presentation completely separate of P4 runtime? Like it introduces completely new primitives, concepts, and APIs.
No, we have add more interfaces, such as adding protocols, or modify the flow table, or the processing logic at runtime. Yeah, we have modified our P4 runtime.
So you've actually gone and added additional APIs for updates and things like that, and to insert into the pipeline.
Yeah.
Right,
Okay.
but we still support the P4 runtime APIs for the table configuration. So that part is the same.
Okay. Okay, I see. That's very interesting. Okay, so you didn't start from like ground up and just say get rid of P4 runtime. We'll do our P4 runtime, I guess. Okay. All right. Okay. Last question. So, and it's more future looking. I see that you analyze the dynamic runtime performance. You looked at pipeline latency and effects of like as you do the update actions on that latency and I'm assuming while traffic is running. What are the future directions you would like to take this work? Like, for example, would it be possible to get this working on a programmable switching ASIC instead of FPGA, or are there other functionalities which you see are missing and you want to extend this work in that direction? What do you see moving forward?
Now we want to make a full stack runtime programmability. In the, for example, in the NICs, in the switches and other network devices, and for both stateless functions and stateful functions. Yeah, we want to make them all to runtime configurable.
Okay.
Yeah.
Are there other targets what you're trying to get to? Like specifically, are you looking at DPUs, or are you thinking about switching ASICs? What's the direction?
Yeah, I would say both are possible. Obviously, a new type of chips is needed. But meanwhile, we also provide a behavior model, which is a software-based switch, just like the BMV2, right? That allows the research community actually to start to play with it, to actually come up with new applications to show its capability. And so beyond that, we do need somebody to actually build such kind of chip. We have an FPGA-based prototype, but that's not enough. We do need the ASIC chips to do that, just like the Tofino here.
Right. Okay. All right. Great. Thank you so much. I didn't have any other questions. Really appreciate you guys coming out and giving this presentation.
Thank you very
right.
much.
Thank
Okay.
you.